Today, we come back with Professor Roberto, now to talk a little bit about maths in biology.
So I'm back. Okay, so I will give a talk which I intend not to be very technical. I'm assuming that you don't work with biological problems. In general, I think this is probably true for more than 90% of you. And therefore, I will begin from the very beginning. I mean, how mathematics comes into biology at all. Because usually if you are, probably you had biology in your high school probably, okay? And then there was no math there, okay? Yeah. And so how come there's mathematics invading biology? Okay? So I call it a gentle introduction in the sense that it will be just an overview. So why is mathematics important in biology? Well, in many problems in biology, you have to count things. Okay? So if you are interested in biodiversity, for instance, and on abundances of species, you want to know if a species is endangered or not or something. Okay? So you have to know the number of individuals. And then you go for observations, and you will have some kind of spreadsheet with the number of individuals. And these numbers are not necessarily constant in time. Right? So there may be time-varying numbers which describe the number of individuals of a population, or it could be also the density of bacteria on a petri dish. Okay? And it could also be not just counting as where are say you are studying a certain species of maybe plants like trees or certain animals, and they roam around the animals, and then you want to describe where they are. So you have the coordinates of them. Yeah? So this will give you numbers, and the numbers will change in time. So you have dynamics. And there we are. It's math. It's already math. It's possible to give a mathematical description, okay, of the dynamics, of the variation that you see in nature. Okay? This can be at the microscopic level and can be at the macroscopic level. Okay? I will rely on examples of macroscopic level connected to ecology and epidemiology, because that's what we here at the Institute work with. But these kind of things I will show you can be also applied for instance, metabolic networks in living beings. Okay, so all this number change, and you can think of, I will describe things. Okay, but the describing is like kinematics. Okay. It's like just saying how the things behave, but you would like more. Okay? You want to write something like that. The time variation should be induced by some biological processes. Okay? So the time variation, let's say, and the number of individuals can be due to birth, death, immigration, and then could also be the spatial variation, which is due to movement. I didn't write it here, but okay. So you'd like something that has some time variation, and in mathematical language. And on the other side, I want to put into mathematical language these processes. Okay? So what should we do? So this will take us to this. Time variation is naturally described by derivatives, either ordinary or partial. And on the other side, you want mathematical expressions for these processes. But you want a mathematical expression for how these processes affect the size of the population or the density of the population. Okay? So, therefore, you want to postulate some laws, okay, that will describe a system. You can think, so when you first get in touch with biological systems and when you talk to biologists, there's something very different usually. People usually are very specific to their system. A person who works with rodents, he doesn't know anything about plants and so on. But we would like to have something more general, like physicists like to have general laws. Although there's no Newton law of biology, there's no such thing. They are not fundamental relations whereupon you can build all the rest. So it's a little bit different, but so we will try to have a perspective which comes like a physicist perspective, a moderate physicist perspective, in the sense that we want to have something general, can be applied to many cases, and but remembering there's no fundamental law which would correspond to Newton's law or quantum mechanics or this kind of thing. Okay, so there is no such thing. So let me go and give you simplest case. Okay, simplest case is like that. You have bacteria dividing, and this is the most simple process of growth of a population. Bacteria divide, and so every individual gives rise to two individuals. Okay, so this if it used by time stacks, this is just a geometric progression. Okay, and if you use time, continuous time processes, this is just given by this equation, okay, where R is the birth rate of individuals. Okay, so what I would like then is say, okay, this is not valid only for my bacteria. We want this to be also valid for other species. Okay? It is not exactly, because bacteria are nice. They divide in two. So each bacteria has like two offsprings. Okay? This is not the same for animals or plants. Okay? But if you do some stochastic processes analysis and go for the mean field and so on, you end up with this. Okay? And in general, this R here is not only the birth rate, it is the birth rate minus the mortality. Okay? So this gives you so this is called the Malthus law. Okay? Malthus. And you know, exponential growth is very crazy. So I would challenge you. Maybe tomorrow you can come with an answer for me. You take one of the simplest bacteria, which is E. coli. And you Google it. And you can get the size and so on. And the population doubles every 20 minutes. How long will it take to cover the whole Earth with E. coli, with a fine layer of E. coli. Okay? Can anybody give a first guess? I know you can. I mean, everybody's thinking of a number. Just open your mouth. A year? Half a day? 4 days? Half a day? Okay. Large variation of answers. Okay? So you can do this calculation. Okay? You need to know the size of E. coli. You need to know the size of the Earth, of the surface of the Earth. Then you need to know how many E. coli you need to cover the Earth. And we start with 1. Okay? We start with 1. Then you know that it doubles every 20 minutes. Therefore, you can calculate this R here by adjusting this. Okay? Because that's easy. And then you can calculate the time for to cover the Earth with that. Okay, so you can check it. It's about depends a little bit of how precise you take the size of the surface of the Earth and so on. Something between 24 and 30 hours. Okay, one day and some hours. Okay, so this is enormous. Right, it's enormous. Yeah. So then you say it cannot be true. Therefore, there's some problem with your law, okay? It says that we will be covered not only with E. coli, but every other species would cover the Earth. Okay? So it's obviously, this law is not meant to be valid beyond a certain range of values of the population. But still, let me make the comment that the idea will be, this is the Malthus law, and population grows exponentially if there's nothing that halts. There's nothing that stops the increase of the population. Okay, so this is very similar to Newton's inertia law. Newton's law of inertia says that the body continues in its motion until if there are no forces on it. Okay? This is also a law that cannot be verified explicitly because there will be always a finite time so you cannot go for always. Okay? And a little bit like that. This law says it goes exponentially until something happens. Okay? And then you start to have fun. What happens? Maybe the size of the place where the population is, and with bacteria would be the size of the petri dish. Maybe there's no enough food for your species, there's no enough light for your trees or something. So there are limiting factors. Okay? So for every population, there should be a limiting factor. Okay? So an equation that takes this into account is this equation. It's called the logistic. Don't ask me why it's called logistic. There's a whole story where I don't have time to tell about this, which says essentially that you would have this, but the ratio is diminished by some quantity, which is negative, and n is always positive, okay? It's the population size. And k is called the carrying capacity. So it's a parameter in the model. Now we have two parameters, okay? When n is close to k, the growth rate tends to 0. When n is very small, it grows exponentially. And that's what you see here. At the beginning, they go for some time, they go together, and then this here slows down and gets to a fixed point, to an asymptotic value, which is equal to k, which is the carrying capacity. Okay? So that's the way to describe modifying the Malthus law in order to describe population that grow and saturate. Right? So, we have already some biological processes. We have birth and death, which come into your parameter R. And you have saturation, which means that the richness of your environment is such that there's a limiting factor for the growth of your population. There are other biological factors, but maybe are not so general as these ones. For instance, you can build models where populations, when they are small, are not viable. For instance, you have a population of certain species have to have a minimum size of the population, otherwise they are too easily predated, and then they disappear. Okay? So you can also model this. You can modify these equations to put this kind of phenomena in your equations. You can put time delay also, maybe. Okay? Time delay is interesting because sometimes the effects are not immediate and so on. You can put time delay. There are a lot of things that you can do with only one population for the moment. Okay, just by the way, this equation is analytically solvable. Okay, and this is one of the only ones that you can actually solve, because if you put n equal to 1 over some other function, n of t, u of t, and you get the equation for u obeys a linear equation, right? Then you solve it, right? But this is the exception. Most of the equations that we will see now a bunch of them, all of them are not solvable, okay? Okay, so, but species are not alone. Species interact, okay? So we can proceed in the simplest way is say that species interact pairwise, one species with the other, because you could have tree-wise or, but let's say pairwise, okay? So, and we can classify the interactions. So one way of classifying these interactions is saying, I have population A and I have population B. Species A or species B. Species, if the interaction is detrimental for A, I put a minus here. And if it benefits B, I put a plus here. What is this? This is usually predation-like things. B is the predator of the prey, A. Biologically, this is not so simple. If there's a biologist here, they would be horrified because there's predation. What you think of, what everybody thinks of predation. Oh, the lion eating the zebra. Okay, that's the cartoon thing. But there are other things like parasitoidism, which is a certain insect that puts eggs into the other species, which may be also an insect or something, and these eggs they grow inside the other guy. So it's not predation in the sense that it's been eaten, but it's detrimental for the host and benefits the parasitoid. So then, so this is predation. If it's detrimental for both, then you say it's competition. Competition is usually not a direct interaction. Competition is you have nutrients, and there are two species. Both consume the nutrients. So if species A consumes nutrients, this is detrimental for species B and vice versa. So this is competition. Okay? And finally, there's mutualism, which is just the best of the worlds. Okay? That the interaction is good for both of them, and the most intuitive and the best example of mutualism is the interaction of a plant with pollinators. Okay? It's beneficial. It benefits both of them. Right? So here's a model that's the simplest model for predation. How is the rationale to understand it? P is predator and V is the prey, like victim. Okay? So the predator, in the absence of the prey, say V is equal to 0, dies out. All the parameters are positive here, okay? So minus mu, that's the mortality times it. So it decreases exponentially, okay? I'm assuming that this predator has only one source of food, which is the prey. It's called specialist predator. Then the prey, in the absence of the predator, grows exponentially. And the interaction is such that it depends on the product of P and V with some coefficients, and such that there is a positive sign for the predator and a negative sign for the prey. And this is called the famous Lotkavolterra system of equations. Okay? And these are not solvable analytically. There's no way of writing down the solution in terms of known functions, but it's not a problem because the solution exists and are unique and everything you want. But then you get only it numerically. You access the solution numerically, and well, here they are. Okay? They are cycles. Okay? So this means that, say, the prey grows and decreases and increases and decreases and increases and decreases, as well as the the predator, and this means that the prediction of the Lotkavolterra type equations is that predator-prey interactions induce cycles in populations. Okay? This has been a very important result in its days because usually people thought that cycles in populations come from environmental interactions, from the seasons, from the day and night, and so on, and not from the intrinsic interaction between species. So this is an important result from the more or less a little bit less than 1 century ago. And here are some data, which are historical data of lynx and hare, the species that I showed you before, these ones. Okay. In the very cold regions of Canada, which also exhibit cycles. Okay, so maybe it's the case for Lotkavolterra-like system. Okay, that's a complicated story, but I won't go into details. So the main prediction, therefore, about your mathematics is predicting a pattern of change. As you don't have usually the values of your parameters of these guys here, beta, alpha, mu, and r, you cannot usually predict exactly the populations, and you don't know the initial conditions, but you can predict the general behavior and see if it fits. Okay, so you predict a pattern, not a function exactly. So competition is built upon the same competition models. It's built upon the same notions as Lotkavolterra. This is called the competitive Lotkavolterra equations. So you have exponential growth, then have here the first time, okay, N1 and N2 are obviously both different species and they're competing, okay? Then there is a saturation, N1 over K1, which is just this part. It's not an interaction part, it's the logistic part for the species N1, and then you have something which is some coefficient which depends on N2 and is negative. And here is vice versa, okay? N1 has a negative effect on N2, and N2 has a negative effect on N1. So there are no cycles here anymore. There's no such thing. And the usual prediction of this model are that unless competition is very weak, in some sense that I don't want to discuss here because I don't have time, the result is that one species eliminates the other. So the fixed points go to, say, species N1 at carrying capacity and N2 at 0, or vice versa. Okay? So this will depend on the coefficients alpha 1 and 2 that I wrote before, so which describe the competitive capacity of the species. So, and this has been very important in biology. So here's more or less what you expect. Here you have two species, which are protozoa. It's Paramecium aurelia, Paramecium caudatum. And you grow them in a culture where you grow them separately. They grow logistically. And you go to their carrying capacity, you grow them, mix it in the same culture, one of them eliminates the other. And these are the real results from 1930s by Georg Gause with the Paramecium aurelia, growth things. This is what it looks like, experimental thing in this kind of biology. It is a lot of noisy data, but they tried kind of saturate here, and when they are grown together in the same culture, one of them eliminates the other. And obviously this has a very important consequences when we don't think only about the protozoa and in general, because this can be a driver of natural selection, right? So the best competitor has advantages and drives out of the system, drives the other competitor to 0. So eliminating this. So this is the basis of natural selection, right? This has to do with competition. So, but this is not enough. This isn't. So let me just make one small comment here. If you really believe in this kind of result, which can be refined and a lot of things, okay, you can actually show if you have n nutrients, you can have n competitors coexisting, but not n plus 1. So the point is, if you expect elimination through competition, why are there so many species in the world? Okay. This is a good question. And this question drove largely ecology and population ecology in the 20th century, in the second part of the 20th century, in the sense that we have to explain the coexistence. And this is interesting because from theory and from experiments, you expect elimination, but you go into nature and you see sometimes coexistence. And how do they coexist? There should be a mechanism, some biological mechanism that makes them coexist. And this has to be explained. It can be several things. Sometimes you have spatial refugia. So one, say A is the best competitor, B isn't good with competition, but it can go to places that the other one can't, so it survives in a refugium. Okay? That's one possibility. Okay? So, and so on and so on. There are a lot of research that has been done on why do we have so many species. Right? So, but again, we have pairwise interactions, but actually the world it's a large and wonderful world. Okay? So species are in networks of interaction and not separated. Okay? So here you have one example of a trophic network. trophic. Trophic means, this name trophic means it's a network of consumers and resources. So you have, for instance, phytoplankton, which is consumed by small planktovorous fish, okay, by benthic invertebrates, and these are consumed by, say, sea ducks or by birds or large fishes, which they are consumed by other large birds, and so on. So you have all the relations. Okay, so this is a kind of trophic network. Okay, so species live in several types of networks, and then the natural question is, how are these networks? Can we map them? Okay, so welcome to the end of the 20th century and the beginning of this century in research on networks on biology. Okay, so can we look at similar systems and maybe discover that the networks associated are the same, are similar? So is there any information that you have by looking at the structure of the network? Okay, so this is, for instance, trophic networks like the ones this is a real thing here from this place for a certain little rock lake. But what is important about this kind of trophic networks, so you see, real networks have a lot of species, okay, is that they are layered. Okay, so trophic, you can define kind of trophic levels. You have the resources that are at the basis. Sometimes this is just plants or phytoplankton, which is primary producers, and then you have one layer, other layer, and then you have maybe the top predators here, which are the ones that have no predator. They are not consumed by any of them. So this is a characteristic, and you can people have been looking for networks in nature, and they actually get something like that. And so you can also look to mutualistic networks, and mutualistic networks are very different. Okay, say here you have an example with animals and plants. So this is a kind of birds and pollinators and the plants and the fruits of the plants. Okay, so they have you can find this kind of nestedness. So you have some species which interact with a lot of other species and many species that have only one interaction. Okay, and here you can have an example of mutualistic network which exhibits modularity. So actually you see that the network gets subdivided and subnetworks. Okay? So this has also been studied extensively nowadays. Okay? So the structure of the network somehow reflects the interaction that are going on. Okay? So then people went on to more and more networks, and this is the network of sexual contacts in a certain city. I don't know, that's a real thing, Colorado Springs. Okay, and the size of the ball is how many sexual interactions sexual partners this person has, and so you see that's very different structure from both the mutualistic or the trophic layers. Okay, you have hubs. Here you have some species, some individuals in this case, that have a lot of partners, and a lot of other guys that have only a few. Okay, and so here I'm showing you the global aviation network. Okay, So why, I mean, the talk is about biology, and this is about planes, okay, transport, okay? But you know, diseases travel by plane, okay? So people travel around. If it's a communicable, transmittable, infectious disease, the disease may travel by plane. So it is important to know these networks, and actually, you can try to predict for instance, if you have an emerging pathogen, as we had in 2000 and something, which was the SARS, which is the acute respiratory syndrome, which there was an outbreak. This is a new thing. Nobody has immunity to this. It's very infectious, and there was an outbreak in Hong Kong. And the next was in Canada, right? So there was a very large concern worldwide about, okay? So this motivated a lot of studies like, if we have something, which are the nodes that are more important to get, to avoid the spread, okay? Which is usually the nodes of the network and so on, okay? So this network structure is important in, well, it's not directly a biological system, but it is important for another biological system, which is infectious disease transmission, okay? And then obviously you can not only look at the structure, but also on the dynamics on networks. You can put differential equation on networks. Each node has a population and has an equation for the population at a certain species. It's connected to the other ones through the adjacency chromatrics of interactions, and then you can play with that, and you can study things like the stability of your network. What if a certain species gets eliminated? Will the network structure continue to be the one that you have, or will there be a cascade of eliminations and have a change of structure? So this, usually there's some species, the keystone species, that if you eliminate them in a trophic network, for instance, then you can have real rearrangement, and you have less species in general. And there are species which are not so important, which if you eliminate them, nothing happens, okay? And this is important to know, because there's going on always species, mainly now with the Anthropocene and so on, there are lots of extinctions, okay? And some of them we want to happen, but we have to be sure they are not important. Like, you know, dengue. Dengue is transmitted by Aedes aegypti. You don't want Aedes aegypti in the world, okay? You want to eliminate it. Right? So you better know if this species is very important for the network, and you have to think twice, but actually it's not. You can safely eliminate, you can extinct Aedes aegypti apparently without any problem, okay? So, but you can play with all of these things with differential equations or whatever, mappings and on the networks, okay? So, my final subject to give this kind of overview is that spatial dynamics. So we have not spoken actually about the spatial aspects. I have talked about how population change in time, but they also change according to their location and space, okay? So, and we know species distributions are not homogeneous. Here I have two examples. Here this is a protozoa, Leishmania, which is transmitted by some kind of it's not exactly an insect, it's a Phlebotomia, and which is responsible for disease called leishmaniosis. And you see here you have the distribution, which is absolutely not homogeneous. And here you have the number of species of reptiles, frequency of reptiles, and so on, which is also completely non-homogeneous. So there is clearly a question of why are there species that are how is it that species are not homogeneously distributed? Why you find a species in a certain point and not at another point? So this connects you with all the biology of the species, like interaction with the environment and so on, and competition. And you would like to understand a little bit of the dynamics of the spatial variations of the species. So the simplest model, which is the model that is the zero ground for this, is to say that now I describe my population by a density, which I can call it rho. Okay? So instead of the number of individuals, I have densities of individuals. And I say that the growth of the population is logistic in this case. It could be otherwise, also it could be just exponential or other models. But then you have this part here, which is the population dynamics stricto sensu. And then you add something here, which is a term of diffusion. Okay? So the simplest hypothesis is that your population density diffuses in space. Okay? You can base this on arguments of stochastic dynamics, for instance. It is approximation. There are lots of more interesting things to do than this, but I won't go into these details. But still, with this equation, you have already some interesting things. So here I have, and it's not a very good movie of the solution. So you can solve this and say you solve it on the real line, okay? So then you get something like that. The population growth saturates and expands. So it's exactly what you expected, yes? Because you have growth, saturation, and diffusion, okay? So you expected this. But the interesting point is that the expansion after some transient time forms a front. And this front travels with constant velocity, a constant speed, okay? So the prediction of this thing is that the expansion is with constant speed. This would not be true if I had only diffusion. If I had only diffusion, you had something else, okay? So constant speed front. That's a qualitative thing about the species. Okay, here I have just to have a second movie, but with the two-dimensional case. The two-dimensional case, you have growth, saturation, and expansion. In this case, we have with symmetry. Okay? So this actually is a very simple model, but there are real world examples about that. So, for instance, here you have data about the invasion of a certain Japanese beetle, okay, in New Jersey, and has been observed for a period of 30 years. Okay, so here are maps which you don't have to, pay attention to the details. What people do in this case is they try to measure at a certain moment of time. They're trying to find the radius of the region where the species is found. And then they observe this year by year. Okay? So if you have constant speed, you have the radius will increase linearly with time. Okay? Constant speed, the space is linear with time. So in that, what you actually got here, after some initial period, which is the transient, because the transient does not have a constant speed. It's the transient. And then you have something which looks pretty much a constant speed. So that's the prediction of the Fisher-Kolmogorov equation, which is the simplest equation for spatial dynamics, which is the invasion speeds are constant, and this is observed in this case. Okay? Okay, this was the simplest case, but space is not homogeneous. Okay? It's not like the space of physics. Space in biology refers to how species interact with the space. Okay? So here you see there's a lot of parts that are, say, this looks like forest, native forest with agriculture, then you have rivers or whatever. You have a lot of things, okay? So it is not homogeneous, okay? And it is not homogeneous naturally and due to human action, okay? Which can lead usually to habitat loss and to fragmentation of your habitats, okay? So, so this is important today. That's the present subject of a lot of research today is how does the habitat loss affect the species abundance and diversity, okay? So you don't have a whole, here you have, for instance, an habitat which has in the Sahel region, it's to the south of the Sahara, which is a desertification region. This is a natural loss of habitat, okay? And you want to know, if you lose habitat, what will happen to your species? Will they decline? Will they be eliminated? Or what will happen? This is important for conservation things, okay? Conservation problems. Then you can also ask a question about, is fragmentation relevant? Which means, fragmentation means maybe you lose a lot of habitat, but still, is it important to know if the habitat is a lot of small pieces or it's just one big piece? Is there a difference in the dynamics of the species, of the abundance and the coexistence, of the diversity of species? So, good question. No answer for the moment. Okay? Then you can also ask yourself, how are patterns formed? Okay, here you see that there are patterns. Okay, so what are the processes that form patterns? And this is also a research subject today of vegetation dynamics, how vegetation patterns are formed. For instance, in the process of desertification, when you go from continuous habitat to a desert, you go to certain stages and of different patterns, okay? And all this spatial dynamics is also important for the management of agri-systems. So how should you manage agriculture in order to avoid species elimination and this kind of thing, okay? So this is usually done with a lot of mathematics, like a reaction diffusion equations, or like a Fisher-Kolmogorov equation, and also with other techniques and so on. Okay? So they are obviously natural and non-natural. This is a kind of non-natural thing, obviously. This is in Pará, and this is the fragmentation and habitat loss due to human activities. This is Serra do Cachimbo. And I still have this slide. You see, it is not a settled question about fragmentation of the. If fragmentation has, what kind of effect fragmentation has on species diversity. Okay? So these are both. This is February 19, this is October 18. So is habitat fragmentation good for biodiversity, or is it bad for biodiversity? So there's a whole discussion, and which is going on and so on. And actually, we are also in our group working with that. So if you get interested, my final question is, you could say, okay, what nice. So I want to study this. Start with mathematical biology and an introduction from Jim Murray, okay? And or with elements of mathematical ecology from Mark Cott. These are nice and fine books that everybody can understand. Right? And the final message is, this is very often quoted, mathematics is biology's next microscope, in the sense that the invention of microscope made a revolution in biology. And this guy, Joel Cohen, is saying mathematics will be the next microscope and better than the microscope. Yeah? And biology is mathematics next physics, in the sense that physics drove a lot of developments in mathematics. All classical mathematics was developed due to problems mainly in mechanics and electromagnetism. All the theory of partial differential equation and so on came from this inspiration of physics. And maybe biology can be the next inspiration for new mathematics, only better. Okay? So, thank you. If you want to contact me, this is my email. Okay?
Thanks again, Roberto. Does anybody have questions?
So thank you for your talk. I'd like to ask, when you do this kind of network between many species, when you do this network between many species, you have a bunch of equations and a bunch of parameters. So can you, with the data, like fit them, because they are not first principle parameters, are they? So can you fit them and determine them confidently?
There's no such thing as fitting these parameters, because what you have when you have a lot of interactions, you have a lot of parameters that you don't know. And if you have a lot of parameters to fit, you can fit anything. Okay? It's called overfitting. Okay? It's a problem, and people from statistics know very well. Okay? And there's the famous joke of von Neumann. Von Neumann said, give me four parameters, and I can draw you an elephant. And if you give me 5, one more, I can make it, I don't know how to say in English, mexer a trompa. So if you have a model that fits any result, it cannot be falsified. So therefore, that's why I insisted about patterns, because patterns are more robust. Okay? Sometimes you have patterns, if you change the parameters, the pattern stays, okay? So patterns of coexistence, patterns of aggregation of species, and so on. So a lot of things that you do is try to look for patterns and explain the patterns, and then you don't have this problem of really fitting. In ecological problems, you have very, very few cases where you really fit data to equations. This can be done sometimes in more mathematical models for epidemiology, for infectious disease dynamics, where usually you have less equations, like you have equations for 3 or 4 functions and some parameters, and many of them you know, then maybe you can go for fitting, even though data in epidemiology is very difficult, because as physicists we are used to have good data. You go on and measure things with 10 significant digits. There's no such thing in ecology, epidemiology, and also even in microscopic biology. Okay, there's no such thing. There are enormous error bars, if you want. There are imperfect data all around, because all of the systems are usually what we call this complex system. If you measure certain variables, but they have a bunch of other ones that you don't even know which ones are important, which are kind of interacting. And this interaction is kind of background noise. Okay? So this data is usually very different from physics, very different.
So you should have an idea by looking at nature and just observing, for example, in the case of E. coli, that the population double, for example, every 20 minutes. So you could like have a guess of the parameter or something like this.
Yeah, in this case, yes. Okay, because this is that what you can do in the lab. The problem is population dynamics in the lab is easier. You have protozoa, bacteria, and some other big, small animals. But you are usually also interested in the field, in the nature, and then things get complicated. Okay? But sometimes you can. For instance, attack rates of predators on prey. This can be measured by observations. Okay? But people look for that. Okay?
Yeah, but in this network case, how can you have a good idea of the parameters that you are using in the equations?
So what you do is, most of the studies define a range of parameters and then they take them randomly. And then they make the study, they make kind of 1,000 realizations of your random, of your network, and they will look for statistical properties that emerge over 1,000 realizations, 5,000 realizations.
But isn't this more or less like a kind of fitting?
Hmm?
Isn't this more or less like a kind of fitting?
Well, it's a different fitting. It's not a deterministic fitting. Okay, it is like okay, we don't fit functions exactly. We look for probabilities, and then you have less parameters, and you will look for robust features of your system and not for the specific features due to some choice of parameters.
Thank you.
It's related to networks as well. I imagine that there's some scale that organize various layers on those networks. It is possible to define some kind of randomization group like appears in condensed matter and quantum field theory
I never saw that.
to try to locate fixed points.
I never saw that about using, the formalism of renormalization group. I guess maybe. Because biology is a lot about scaling up from micro to macro, a lot of things, okay? You can look at very microscopic level and go up to very macroscopic one, like going from cells to ecosystems. But I don't know which would be the variables that you would actually want to know and so on. So it's not clear. The idea is there, but how to really formulate the problem in a concrete scenario, it's not very clear.
Right.
Hi. So I have a comment and a question. My comment is that equation is the equation we use for nuclear reactions involving different chemical species.
Yeah.
So the connection between physics and biology is already there.
Yeah.
So I found that really interesting. That's why I wanted to make a comment.
Yeah, the comment I can make on this is about the history of mathematical biology, okay? So one of the important formulators is Alfred Lotka. Alfred Lotka was not a biologist, right? He was a chemist. And he was a physicist. This guy's very crazy. It's worth hearing to that. He was born of American parents in Ukraine. Okay, so he was an American citizen born in Ukraine. And he went to study in England. So he was a student initially of a guy that you have heard about. It's this pointing vector was his professor. And then he moved to Germany, I think to München, to work with Ostwald from chemical physics, physical chemistry. All right. Okay, anything? So Ostwald is famous for being the serious scientist, the last serious scientist that did not agree with the atomic hypothesis. Okay? At the end of the life, he changed his mind. And so what they had were reactions, and you have concentration of reactions, and you have this kind of things like the Lotkavolterra equations, and yet in this products, like you had this kind of products. Okay, it's called mass action, and so they had this, and then Lotka moved on and went to the United States, and he went to work in a lab, a biology lab, from a very important guy at Johns Hopkins, and who was working with flies, population dynamics of flies. Okay, so and he wrote a book, and his intention was to formulate biology at the population level, like chemistry is formulated when you have this kind of thing. So it comes exactly from this kind of kinetics.
And I have a question. Maybe you made a comment during the talk, but how you introduce an environmental event? For instance, can you have a model to reproduce extinction of the dinosaurs, for instance?
Yeah, well, people have this kind of thing, but I mean, this depends on that. Like, models, models are as good as the biology that you put in the model, okay? So you have an extinction event, you say, okay, there's a meteor. I mean, this is obviously not even necessary to model, okay? So, so what you have is you can introduce external perturbations and heterogeneity, okay? So you can do this. For instance, saying I have this kind of equations, but actually this depends on the position. Or this depends on the position or whatever. The diffusion coefficient, the interaction coefficient can depend on position. They can be random. Then you can have perturbations, environmental perturbations that perturb some of the parameters, and so on and so on. So people do this kind of thing in sometimes simple models. And yeah, you can study this.
Thank you.
Hi.
Hi.
I like the sentence presented in the previous slide about how biology is new mathematics, physics. Yeah. What would be some developments in mathematics required by biology that go beyond like what you showed us that is pretty much derivatives?
Yeah. Okay. Yeah. What I showed is actually very simple math. So the guy is very optimistic, okay? John Cohen, it's a very important biologist actually, but he's very, I mean, this is a perspective thing. But one example is evolutionary game theory. So you have game theory, and you have adaptation of game theory to explain evolutionary processes, okay? So this is inspired. I mean, game theory existed before being applied to evolutionary problems, but evolutionary problems inspired new developments and to something which is now called evolutionary game theory. Okay? That's an example. Okay? Different mathematics, it's not just different differential equations and so on. Okay? It is true, all my examples are very pedestrian with differential equations, and a lot of the mathematics we as physicists tend to use is the one that we know, which is 19th century mathematics usually. But so people's perspective that maybe there will be some new developments in areas, for instance, in computation with bioinformatics. Maybe you have to develop new notions in order to cope with big data of genomics, of proteomics, and so on. But actually, I'm just saying this in the large, I don't know the details, but I have heard that actually there are people that there are developments in computation that maybe are really new and are adapted to certain biological processes.
Any more questions?
If not, thank you again.
Okay, thank you.
And Peter has announcements.
Okay, so two basic invitations. The first one, if you enjoyed this lecture, there are open the subscriptions for Kraenkel Summer School. So in January, there's a mathematical biology program here in this auditorium. It's 1 week courses with Kraenkel, all about this.
Just let me explain. This is very different summer school, okay? Very different in the sense that the summer school is 1 week and you have only 1.5 hours of lectures per day, and the rest of the time you are working in projects, group projects with 6 persons, and the number of biologists and the number of physicists or mathematicians is the same. So we're really interacting with the real biologists, okay, and so on. And this is very exciting for a lot of people. So you're invited to do this. And then there's a second school for more advanced part, which will be about ecology and communities and so on. So.
And the second invitation is that right now the metro is very crowded to leave and go home.